Games can have dozens or even hundreds of NPCs navigating their way through the game's world. There is no way all those paths are manually set by developers. It would be tedious and just wouldn't work, as in most games characters have to react to the player's actions. So, how do NPCs find their way around? For the human brain, this might seem trivial, like the path is just there, but when it comes to writing it down, coming up with a precise set of steps that will produce a path is a bit harder. Such an algorithm has to work for every possible path combination there is. It should also be fast enough to be useful in the video game's context. In this video we will take a look into the A*, one of the most successful and widely used algorithms for NPCs AI programming. Even though today the A* algorithm is widely used in video games, it wasn't originally designed with the virtual entertainment in mind. The algorithm was first published in 1968 in a paper called A Formal Basis for the Heuristic Determination of Minimum Cost Paths, so a total of 4 years before Pong, one of the first commercial games, was released. It was created as part of Stanford's University Shaky project. The main goal of this research was to create a general-purpose robot and use it as a platform for testing and developing new robotics and AI ideas. The Shaky code allowed it to scan its environment and traverse from goal to goal. Such logic required a sophisticated and performant pathfinding algorithm, and A* was what the researchers came up with. In video games, the A* wasn't adapted until much later, mostly due to hardware limitations. Doing pathfinding almost in real time within dynamic environment wasn't something that devices of the past could handle. There were some quite successful attempts to include pathfinding into games, for example Pac-Man, but solutions that were used in those games were very limited and worked only in very restricted environments. It was enough for simple games, but when the scale of productions grew drastically in the 90s, better pathfinding solutions were needed. I couldn't find exact information which was the first game ever to use the A* algorithm specifically, but Diablo is mentioned as one of the contestants. In its core, the A* algorithm operates on graphs. We can picture graph as a set of vertices connected by edges. Other popular names for those vertices which I'll be using are nodes or simply points. The core idea of this algorithm goes as follows. Find the shortest path from the start node to the end goal. There's another famous pathfinding algorithm you may have heard of, the Dijkstra algorithm, named after its inventor, Dutch computer scientist Edsger Dijkstra. In some sense, the A* is derived from the Dijkstra algorithm, with the addition of the heuristic function. This function helps to guide the algorithm through nodes that are better candidates to form shortest path. The Dijkstra algorithm treats all possible paths as equal, while A* can weigh different options and choose more plausible ones. And that's where its efficiency comes from. The fact that the A* algorithm works on graphs means that the game space has to be divided in some way which can be represented by graph. There are many approaches to this problem, and these are some of the most common ones. Gothic games use a literal graph, which had to be manually added to the world by the developers. In this game, nodes are named waypoints. NPCs use a web of waypoints to navigate their way through the world. Gothic's NPCs' behavior revolves around so-called routines. Those routines take place at concrete waypoints. So, when developers want an NPC to walk somewhere else, they change their routine. If the routine takes place at a different waypoint, NPCs will first navigate their way to the designated place. There are more rules to the character's behavior. If they happen to be in a place with no waypoints, they will first scan for ones that are nearby, and then move towards one which is closest to their destination. If there's trouble getting to this waypoint, they will try a different one. There's also a simple collision avoidance mechanism in place, but this kind of techniques are a broad topic for its own video. This approach has some limitations. Firstly, it requires quite a bit of manual labor. Another issue is that basing logic on the nearby waypoints make NPCs unaware of vertical obstacles, which can produce AI glitches like walking into a wall. Next, the web of waypoints is pretty sparse, so sometimes when an NPC moves from point to point, the turns and paths taken looks unnatural. But overall, it's pretty good solution which mostly gets work done and does not require fancy tooling. Games with discrete movement naturally work well with the A-star algorithm. First, each field that a character can walk into should be treated as a separate graph node. Now, nodes should be connected in a way that represent the degree of movement available in a given game. In Pumpkin Man, characters can move in 4 directions, so each node is connected with maximum of 4 different nodes. Those two methods are pretty simple ones. Many modern games use far more sophisticated techniques, which combine different algorithms. Also, search space can have multiple layers. But still, those systems will use the A-star or one of its modifications in some capacity. One of the popular methods of implementing pathfinding today is using nav meshes. This is a technique that uses the geometry of the game's world itself to produce the pathfinding graph. Such a graph closely resembles the actual shape and details of terrain. This can produce better results and has the possibility to save a lot of manual labor. For example, in the Witcher 3 engine there is an automatic generation of nav meshes built in, which reduces the need for level designers to plan navigation by hand. This technique, even though it produces better results, requires more upfront work with designing and implementing algorithms for nav mesh generation. Now, how does the A-star algorithm work step by step? For example, if we want to find a path between those two vertices. First, we need to assign a length to every edge in the graph. Then we will assign parameters to every node. Each node is described by 3 parameters. Those parameters are g. This is a cost of reaching a given node from the start. So the starting node has g equal to 0. The second node in the path has g equal to distance between two nodes. The third has g equal to distance between itself and previous node, plus g of previous node, and so on. At the start, only the first node has g assigned, as it's unknown which way the path will go. The second parameter is called h, and it stands for heuristic. It is an estimated cost from given node to finish node, which basically means that this value is an educated guess of how far it is from a given node to the end. There are many approaches to calculating heuristic of graph nodes, the choice of which method to use is strongly influenced by the freedom of character's movement in given game. If character can move at any angle, the best approach is using Euclidean distance, which is just a distance in a straight line between 2 points. In games with a 4-way grid-based movement, a better approach is to use the so-called Manhattan method, where the heuristic function value is a sum of the absolute differences of x and y coordinates of given points. From this depiction, it's clear why the heuristic is just a guess of how close a given node is to finish. If there is any obstacle on the way, then this guess will be wrong, and the algorithm will be working longer as a result. Still, a well-chosen heuristic method will shorten the algorithm runtime in most common cases. The last parameter describing nodes is f-score. The value of this parameter is simply a sum of g and h parameters. The lower the f-score, the better candidate for search a given node is. Each node can also have a single parent node. This parent node will be used to build a path after the algorithm completes its run. At the algorithm start, there are 2 empty lists. One is called an open list and the second closed list. The start node is added to the open list. The algorithm is running in a loop. First, the node with the lowest f-score in the open list is found. At the start there is just one node in this list. This node is removed from the open list and is set as currently processed node. Now the processed node is set as parent for each node that is adjacent to it. Each of those adjacent nodes has calculated its g-value, which is simply a g-value of the processed node plus the distance between those two nodes. Each neighbor node has also its heuristic value calculated, and the f-score is set using both g and h value. After that, this node is added to the open list. After processing all adjacent nodes, the processed node is added to the closed list. Now, the process repeats. The first node with the lowest f-score is found in the open list. Then parameters are calculated for all neighbors which aren't already added to the closed list. Then the processed node is added to the closed list. There are also some edge cases which need to be handled. Mostly, if the node at the top of the list is the same as the finish node, then it means that the path has been found. On the other hand, if the open list is empty and the algorithm didn't reach the end node, then simply no path exists between those two nodes. Also, if one of the adjacent nodes to the currently processed one is already in the open list, it's required to recalculate its f-score using this node as parent. If the score happens to be lower than the one currently set, then a new route should be set. If you are interested in details of how to implement the A-star algorithm yourself, I highly recommend the sources I linked in the description. I want to take a moment to thank every one of you. We recently reached 1000 subscribers, and it's a support I truly appreciate. So once more, thank you for watching, subscribe for more and leave a comment if you have any questions. I will see you in the next video. Have a nice day.